Hello there, ATS EVS 105 students. Dr. Schragi here, and I am ready to talk to you a little bit about our next lecture in the class, and that's climate sensitivity. When we talk about climate sensitivity, I mean, it's kind of important to put this into context in this module, okay? So far in this module, we've been talking about two main things: the radiative forces that drive the climate, and the feedbacks that can work to amplify or ameliorate the climate changes that were driven by the radiative forcings. And your book makes an attempt for about a page or two to try to show you how complicated the math of a feedback can get. And honestly, the math gets so complicated so fast, and what they're trying to show you is actually quite a simple feedback. It just isn't a really easy way to discover how sensitive the climate is to these changes. There had to be a better way to do this. It might not actually be, I wrote it in here, it has to be an easier way to do this. Easier to comprehend anyway, okay? Not necessarily the math is easier, but something easier to think about. And so, what we're trying to get at, the context here might be helpful. What we're trying to get at here is a consistent way of describing the change in climate that will occur as a consequence of something that happens. If we do something, we put a certain amount of greenhouse gases in the atmosphere. If we create a feedback of a certain size, or if we create a radiative forcing of a certain size, what will be the result of that? I mean, that's conceptually, that's what we're trying to get at here, without trying to get into doing a whole bunch of math or something like that. And so if we're trying to figure out something like, what if I increase the amount of greenhouse gases by a certain amount, that should be something that we can do. And in fact, that's a thought experiment and a numerical experiment that climate scientists have done. They like to do these sort of double carbon dioxide concentration experiments where they ask themselves, how much would the climate change if we increase the carbon dioxide concentration in the atmosphere from its pre-industrial level of 280 parts per million to twice that, or 560 parts per million. Just to refresh your memory back from the scenarios lecture in an earlier module, 560 parts per million? That's probably going to happen. We are already a little over 400 parts per million. We are well on our way to 560. It seems even the more optimistic scenarios that you learned about in the scenarios lecture didn't really miss 560 parts per million by all that much. So this is probably going to happen here. Well, it turns out we can take our ideas that we've been learning about radiative transfer through the Earth's atmosphere and how much each layer of the atmosphere is absorbing and emitting and so on, and we can come up with the energy balance and determine, based on solid physics, there's no politics or anything like that involved, it's solid science, we can figure out what the radiative forcing is of twice as much carbon dioxide as there was before. And if you take that radiative forcing, you can actually compute what the change in the surface temperature would have to be in order to return to energy balance, as we did in earlier lectures of this module. And you can find that the change in the temperature would be about 1.2 degrees Celsius if we doubled the carbon dioxide in the atmosphere. Now, a climate change of 1.2 degrees Celsius is nothing to sneeze at. That's a significant climate change. But frankly, it's about what we've already seen. It just seems like, okay, it's a problem, but it's a manageable problem, right? We can maybe deal with 1.2 degrees Celsius. But here's the deal. That's just the radiative forcing of the carbon dioxide itself. This change in temperature sets in motion feedbacks, both positive feedbacks like the water vapor feedback, and admittedly negative feedbacks like the vegetation feedbacks, but all of those feedbacks are going to be working either to amplify this initial temperature change of 1.2 degrees Celsius or ameliorate it and push the climate system back towards the long-term average. Well, sure, things like the weathering thermostat will try to shift the climate back towards its long-term average on the order of millions of years. On the other hand, there's these fast feedbacks like water vapor that are going to be amplifying this radiative forcing. If you use the kinds of relatively simple analysis techniques that the book is trying to show you at the beginning of this reading, which I don't want you to actually have to work through all that math or anything like that, you can show that the result of these feedbacks will be to amplify the climate change to a range of about 2 to 4 degrees Celsius based on a doubling of carbon dioxide. 2 to 4 degrees Celsius is a pretty big temperature change. That is certainly into the range where, we're going to be worried about sea level change. We're going to be worried about ice sheets melting, changes in ocean circulations, changes in habitats of creatures, and so on. That's a pretty big temperature change, and that's just using this relatively primitive set of math that the book is trying to show you in the beginning of this reading. A more technical analysis of the feedbacks using models and so on done by climate scientists can kind of show that actually that range isn't quite so clear. It might be more like 2 to 4.5 degrees Celsius is a good range of expected outcomes if we double the amount of carbon dioxide in the atmosphere. And overall, our best estimate, and I'll show you later how we got to this best estimate of how much climate change would result from doubling carbon dioxide, is about 3 degrees Celsius, which is a lot more climate change than we've seen already. More importantly, as you'll see in a little bit, we can kind of get a sense of how likely different outcomes are. And it turns out to be extremely unlikely in a doubled carbon dioxide situation where we would have less than 1.5 degrees Celsius of climate change. These very manageable, small climate changes don't seem very likely to happen if we double carbon dioxide. And remember, we're likely to do a whole lot worse than double carbon dioxide, okay? Some of those scenarios that you looked at on that day, I should have brought the slide up here, they had concentrations of 800 parts per million or 1,000 parts per million, way more than 560. But just doubling the carbon dioxide, we've got some pretty negative outcomes there. But the truth is we don't entirely know. We don't entirely know how sensitive the climate is to these changes. We need a way of actually quantifying this. We need a way of saying when we made some change, like doubling the carbon dioxide, what was the change in the temperature that resulted? And see, in this case here, by doubling carbon dioxide, we saw that our best estimate was 3 degrees Celsius. And that is a measure then of how sensitive the climate system is to carbon dioxide. I mean, climate change deniers might say that we can put all the carbon dioxide in the atmosphere we want and it won't make a temperature change. Well, then they're saying the atmosphere is not very sensitive to changes in carbon dioxide. They're factually wrong, but that doesn't change the fact that people advance that opinion. All semester long, we've been trying to discuss this idea of changes in the physics that are driving the climate system, and we've been saying this in terms of things like radiation balance and forcings and feedbacks. But now we have a way to actually talk about how much this is moving the climate. Sensitivity tells us, all right, we now know, based on solid physics, add this much carbon dioxide, you get this many watts per square meter of radiative forcing. Sensitivity then says, by doing this analysis, we can figure out how big the temperature change is going to be. Now, one of the drawbacks of that double CO2 type experiment, like what we just kind of walked through there, is that carbon dioxide is not the only anthropogenic greenhouse gas that we are worried about. We can be worried about other greenhouse gases that are, occur in trace amounts in the atmosphere, like methane, tropospheric ozone, stratospheric water vapor, nitrous oxide, halocarbons, as well as the other anthropogenic changes that can drive the climate, like land use changes and so on, that all affect the climate too. But now we have a way we could talk about it. If our changes in the land use drive a certain radiative forcing of so many watts per square meter, we should be able to figure out how big of a temperature change it's going to be. And this is neat. This is a nice way of taking this apples to apples type way of comparing. Remember before, let's backtrack on this here. We were talking earlier in the semester about, oh my goodness, we've increased methane from this many parts per billion to this many parts per billion. Or we increased carbon dioxide from this many parts per million to this many parts per million. Of course, carbon dioxide molecules aren't as effective as greenhouse gases as these are. Yeah, it was too much to keep track of. This isn't apples to apples. We don't know how to compare this much, how much climate change was due to methane, how much was due to carbon dioxide, how much, we needed a way that compared them in the same units, apples to apples. And this is a very powerful scientific idea here. Let's think about what the units of this measure of sensitivity are going to need to be. Well, all of our radiative forcings, whether they were by carbon dioxide or stratospheric water vapor or changes in land use or whatever, aerosols or whatever, they all had common units. They were all in units of watts per square meter. The changes in carbon dioxide would have units of like parts per million or whatever, but the radiative forcing that resulted in that was the result of that had units of watts per square meter. All of these radiative forcings themselves result in a change in the global mean temperature of the Earth in units of degrees Celsius. So, if we wanted to do this, we could say that a good way to describe our climate sensitivity that we're trying to come up with is going to have units of degrees Celsius per watt per square meter. Now, those are awkward units. They're kind of awful, to be honest. Degrees Celsius per watt per square meter. Where are we going to get this number? This number is going to come to us from the models. This is not something that we can go outside and measure. We can't measure climate sensitivity. We use our models and we say how sensitive is the model. If we increase the radiative forcing a certain number of watts per square meter, how big of a temperature change do we get? And so if we actually take a large number of models and a large number of scenarios and we try them all and we kind of come up with a sense of what is the range of possible climate sensitivities between all of our different models, we have a whole ensemble of models running a whole ensemble of different scenarios. We find that overall our best estimate of climate sensitivity, it turns out to be 0.75 degrees Celsius per watt per square meter, which is an awful set of units, and it's hard to pick out what this exactly means. Let's actually take this apart. In other words, for every 1 watt per square meter that we set up of a radiative forcing of the climate, like we had numbers like about 1.6 watt per square meter was due to carbon dioxide, and about 0.2 watt per square meter was about land use changes, and so on. For every 1 watt per square meter of radiative forcing, quite regardless of what caused that radiative forcing, the mean temperature of the Earth will shift by about 0.75 degrees Celsius. Oh, well, that's kind of handy, isn't it? I no longer care what's causing the climate change. Anything from changes in the Earth's orbit, to changes in the output of the sun, to changes in the albedo of the Earth, to stratospheric water vapor, to mineral dust in the atmosphere. I don't care. As long as I can put its radiative forcing into units of watts per square meter, I now know how big the climate change will be. Because if I have 1 watt per square meter of change, it will change the temperature of the Earth by 0.75 degrees Celsius. At least that's our best estimate of the climate sensitivity. And if I change the energy balance of the Earth by 2 watts per square meter, it'll be 2 times 0.75 or 1.5 degrees Celsius of warming. This is neat. This is handy. This is powerful. It gives us ways to think about policy questions. For example, back in November of 2011, there was this big Paris climate change conference that was all on the news and so on, and one of the resolutions of the conference was that all the nations of the Earth were going to work to keep climate change less than 2 degrees Celsius. What a wonderful, admirable goal. And if you crank that number into our idea of the climate sensitivity, where the climate sensitivity is about 0.75 degrees Celsius for every 1 watt per square meter, you can work backward through the math and figure out that that means we need to keep the radiative forcings that are caused by anthropogenic changes down to 2.67 watts per square meter. In other words, we can, as long as we keep our total radiative forcings less than 2.67 watts per square meter, we should be able to keep the global climate change under about 2 degrees Celsius, which at first glance doesn't look all that bad. I mean, I just swiped here a slide from the first lecture in this module, and the number I want you to draw your attention to there is that the sum of all radiative forcings on the climate since the Industrial Revolution was 1.6 watts per square meter. Oh, well, that's actually not so bad. I mean, that's 2 centuries of burning fossil fuels and tearing down forests and putting aerosols in the atmosphere, and some of those things were positive radiative forcings and some were negative, but you know what? After 2 centuries of doing this, we've kept it to, considerably less than 2.67 watts per square meter. Maybe this isn't so bad. Maybe this is doable. Maybe the world's not quite as messed up as we thought, but then a little subtle thing catches in here. That number of 1.6 watts per square meter, that is the anthropogenic radiative forcing, that's just the forcing, that's not the feedbacks. That number there was not and then the water vapor feedback will amplify that change. Admittedly, aerosols will also work to offset some of that warming and so on, but in general, we're going to blow way past that number. Okay, the total radiative, the change in the energy budget due to anthropogenic activity is already more like 4 or 5 watts per square meter, and we need to keep our radiative forcing of the climate to less than 2.67 watts per square meter. Yeah, we have in fact already Oh, where am I at here? Oh, hold on. There we go. In other words, just to use a vocabulary word from earlier in the module, our committed warming is already greater than 2 degrees Celsius. In other words, we've already made the changes to the Earth's environment by putting greenhouse gases in the atmosphere like carbon dioxide, methane, halocarbons, etc. Made the changes to the albedo of the Earth and so on. That between those and the corresponding natural, feedbacks like the water vapor feedback and so on, we already have more than 2 degrees of warming in the pipeline. There's nothing we can do about it. If we stopped burning fossil fuels today, we couldn't stop the planet from warming more than 2 degrees Celsius. That's bad. That's really bad. And all of that is contingent on our idea that hopefully our understanding of this climate sensitivity is correct, and that a good value of the climate sensitivity is 0.75 degrees Celsius per watt per square meter. Maybe that's not a great one. Maybe our, maybe that climate sensitivity isn't that big. Maybe our models are wrong and the planet doesn't warm as much for every watt per square meter. I mean, some models showed a little bit higher climate sensitivity, some showed a little smaller. Maybe our best guess is just not that good. Okay, then maybe there is time to fix this. Okay, but maybe the best guess is too low. Maybe the real climate sensitivity is even bigger. And in fact, there's a good chance that maybe for every watt per square meter of anthropogenic radiative forcing on the surface of the Earth, there'll be an even bigger temperature change. Oh my. We better get a handle on what that means. And in fact, I kind of stole this picture from, I believe this was in the IPCC, although I think it might have been in your book or on your book's website too. I'm not quite sure where I got this copy of it. But what this was an ensemble of climate models. We ran a whole bunch of climate models for the doubled carbon dioxide concentration scenario. All of the models had a doubling of carbon dioxide due to anthropogenic reasons, and then they let it run. All the models have slightly different ways of calculating the water vapor feedback and the vegetation feedback and all those other feedbacks and so on that you learned about. And what happened then is we just made a histogram. Okay, every model had a certain change in the global temperature based on the doubling of carbon dioxide. And we just made a histogram. And you can see that a whole lot of these models showed that climate change was less sensitive to radiative forcing than we thought. Like the ones I have circled there in red or boxed in there in pink or whatever, those are the ones with less than 3 degrees Celsius of warming, and then when we doubled the carbon dioxide. So some models actually did say the planet doesn't warm as much as that. And that, for the amount of radiative forcing we have had, the planet won't warm that much. Okay, good. That's good news to know. But I want to draw your attention to this rather large tail in the distribution of the histogram out here to the right. Some of the models suggest that the climate is more sensitive to a radiative forcing, with more than 6 degrees Celsius of warming. I mean, some real climate models came up with changes in the global temperature if we increase the amount of carbon dioxide to double the pre-industrial values, which is almost certainly going to happen even under optimistic scenarios. Holy smokes, some models came up with these huge changes, like 10 degrees Celsius. That is a big temperature change. Uh-oh. Now, yeah, you can see where that idea of the best estimate came from. The best estimate, most of the models come up with about 3 to 3.5 degrees Celsius temperature change if carbon dioxide concentrations doubled from pre-industrial levels. You can see now where that number I gave you way back on like the second or third slide came from. Our best guess, based on a whole ensemble of climate models, is that the number is between 3 and 3.5. I think 3 is the fairly accepted number with a finer analysis than this, okay? But I want you to show you something that's really scary about this plot. Boy, there's a whole world of bloggers and radio hosts and cable news pundits and so on who want to tell you that there'll be almost no climate change due to carbon dioxide increases. But look what actually the models say. Literally no models showed that there would be less than 1.5 degrees Celsius of warming when we doubled the carbon dioxide concentrations in the atmosphere. Literally none. There's no chance that's what's going to happen, unless we're wildly wrong with the models, which we're not. Oh, literally no chance of that nice outcome. I mean, yeah, I understand. People want there to not be any consequence of burning all these fossil fuels and so on, but the models tell us that's not going to happen. Okay? Meanwhile, let's go visit the scary end of the tail here, of the distribution. Some of the models suggest that climate sensitivity could be so high that the climate change in the double carbon dioxide scenario could be between 8 and 12 degrees Celsius. That is a warming of 14 to 21 degrees Celsius. That's a civilization ender. Okay, we can't live on the modern economy, the modern agriculture, modern fishing. Nothing about how our food works, our climate, or energy distribution, nothing works in a planet that is warmed by 21 degrees Fahrenheit. Okay, those scenarios, admittedly, aren't very likely. Not that many models came up with those scenarios, but a lot more models came up with these scenarios than these relatively happy scenarios where nothing much happens. That should scare you. Okay. That is intended to scare you. That, and not as in like they did the science intending to scare you. It's to show you that that is a very serious possibility. Okay, these are unpleasant scenarios. You know, unpleasant in the sense of famine, okay? Or wars over water rights and things like that. And species going extinct. Unpleasant. These are civilization enders, okay? We can't live in this world. And that's a real possibility merely by doubling carbon dioxide. We're going to do a lot worse than doubling carbon dioxide. These horrible outcomes are far more likely than the moderate outcomes that, frankly, most people are hoping for. That should give you pause. And speaking of pausing, let's actually ask a couple quick questions before you would move on to the next lecture. Question 1. Our best estimate of the amount of warming that will occur globally if carbon dioxide concentration increases to 560 parts per million is about 0.3, 3, 8, or 12 degrees Celsius. How much warming are we talking about with a, realistic, if perhaps optimistic scenario of merely doubling carbon dioxide from pre-industrial levels? All right, make your choice for one of these 4 options and get a little feedback before you move on to question 2.